Welcome back to the thermodynamics course. The lecture today is the third lecture in the three-part lecture for the thermodynamic math lab. And on the PowerPoint, we'll look at the topics that we'll look at today. That will include the vapor pressure and saturation vapor pressure and the use of the Clausius-Clapeyron equation. Clausius-Clapeyron equation is the equation that's used to determine what the relative humidity is of the air. We'll also be looking at the mixing ratio equation, latent heat problems, the virtual temperature, dew point depression, relative humidity, lapse rates in the troposphere, equivalent temperature, equivalent potential temperature, which is also known as theta E, and the hydrostatic equation. We'll start off with defining vapor pressure and saturation vapor pressure. The vapor pressure is the actual vapor pressure in the air expressed in millibars. So it's going to use the dew point value to find out at that dew point how much moisture is in the air. And for the saturation vapor pressure, that's measured with respect to the temperature. So maximum possible vapor pressure for a given temperature in the air expressed in millibars. The Clausius-Clapeyron equation. What this equation does is it relates the saturation vapor pressure to the temperature. It can also be used to relate the vapor pressure to the dew point. And next we'll take a look at this equation. It has a natural log function in it, which we have learned how to solve those. And to solve the Clausius-Clapeyron equation also requires using the exponential function. Here are the different terms in the equation. The e to the s value is the saturation vapor pressure. The L is the latent heat value of vaporization. And this value does vary slightly with temperature, but in this class we're going to hold it as a constant to keep things simple. It's 2.453 times 10 to the 6 joules per kilogram. RV is the gas constant for moist air, 461 joules per kilogram. And the temperature is plugged into the equation at this point right here. And the temperature is always going to be in units of Kelvin. And as I mentioned, this L value, latent heat of vaporization, does vary slightly with temperature, but we're going to hold it as a constant when we're solving these equations. This L divided by RV here, if you take those two constants and divide them together, that produces that value of 5,321.041215. So again, this equation, we have the natural log function of e to the s divided by 6.11 is equal to L over RV times 1 over 273 minus 1 divided by the temperature. On the overhead camera, we'll look at an example of solving the Clausius-Clapeyron equation. We're going to be given a temperature of 20 degrees Celsius. And 20 degrees Celsius, once you have the temperature, that needs to be converted into kelvins. 20 degrees Celsius is 293 Kelvin. And here is the Clausius-Clapeyron equation we looked at on the PowerPoint. And what we need to do is plug in the value for temperature, this 293, in for T, and solve. As I mentioned, the L over RV value is equal to 5,321.041215, and that's multiplied by 1 divided by 273 minus 1 divided by 293. This right here, the 1 divided by 273 minus 1 divided by 293, that number comes out to this number that's given here, a fairly small number. And then it's multiplied by the 5,321 0.041215 value to get this number here. So you'll want to practice this on the calculator. Make sure you're able to get these numbers here that I have down, so make sure you write down this information. And on the left side of the equation, we still have the natural log function of the saturation vapor pressure divided by 6.11. What we're going to do next to solve this is take the exponent of each side. And when we take the exponent of each side, on the right side, we're going to have this e, which stands for the exponential function of this number that we had here. And on the left side of the equation, there's a mathematical rule that we went over in the first lecture, that if you have an exponent of a natural log function, then they cancel each other out. So we're left with just the saturation vapor pressure divided by 6.11 on the left side of the equation. In the scientific calculator, you put in this number and find the exponent of that number, and you'll get this number here, the 3.782719667. And make sure that you keep as many digits that the calculator will give you when solving this. You don't want to do any rounding until the very end. Next, we'll multiply each side of the equation by 6.11 so that we have the saturation vapor pressure on just one side of the equation. And after that is done, we have this value here multiplied by 6.11, we end up with 23.1 millibars. So at a temperature of 20 degrees Celsius, 293 Kelvin, the maximum amount of moisture that can be in the air, the pressure from that maximum amount of moisture, will be 23.1 millibars. Next on the PowerPoint, we'll go over the mixing ratio equation. The equation for the mixing ratio is W. W stands for mixing ratio, and that is equal to 0.622 times the vapor pressure, and then divided by the pressure of the air minus the vapor pressure. So the W is the mixing ratio in kilograms of water vapor per kilogram of dry air. So that's the definition of the mixing ratio. So you have your mass of moisture divided by the mass of dry air. The 0.622 in the equation comes from RD divided by RV. So these are two gas constants and the ratio of those gas constants. E is our vapor pressure in millibars. P is the air pressure, also in millibars. And the P minus E is the pressure from the dry air alone. So in our equation for mixing ratio, it was, we were dividing by the kilograms of dry air. So to make this air dry, we subtract off the pressure that's being produced from the water vapor. If we wanted to rewrite this equation where E, the vapor pressure, is on one side of the equation, we can do that. We can rearrange this equation here to get this equation. The vapor pressure is equal to the mixing ratio times the pressure, and then divided by 0.622 plus the mixing ratio. Next, we'll look at a mixing ratio example. So our example problem at 850 millibars, what is the mixing ratio when the vapor pressure is 7 millibars? And so we have our equation here, and we'll plug our knowns into the equation and solve. Our value of vapor pressure is 7 millibars, so we'll take 7 times 0.622, and then divide that by, we need to find the pressure of the dry air, so we take 850 millibars and subtract off 7 millibars. And that produces these two numbers that we have down here that are divided by each other. And once they're divided by each other, that'll produce a value of 0.00516 kilograms per kilogram. Often the mixing ratio will be written as grams per kilogram. And to do that, you multiply this value by 1,000. So for example, often it'll be expressed in grams per kilogram, since this number is easier to write than having to write these zeros here. So it's 5.16 grams per kilogram. Next, we'll look at latent heat problems. There are three sets of latent heat variables for water that you're going to need to know for this course. The first set is melting and freezing. With melting, the direction of heat flow is into the water, and with freezing, the direction of heat flow is away from the water. And the amount of heat that's transferred in both these processes is 3.34 times 10 to the fifth joules per kilogram. So the value is the same, it's just the direction of the heat flow is the opposite between melting and freezing. Evaporation and condensation are the second set. With evaporation, the direction of heat flow is into the water. And so since the water is taking the heat out of the air, that's going to cause the surrounding air to cool. So the evaporation process causes cooling. Whereas with the condensation process, it's the opposite. The direction of the heat flow is away from the water. So when condensation occurs, that is going to add some heat to the air. And that's a very important process in meteorology when it comes to thunderstorm development. The latent heat of condensation is going to add heat to the developing updrafts for the thunderstorms. The amount of heat transferred in both these processes is 2.5 times 10 to the 6 joules per kilogram. One more set to look at. These are sublimation and deposition. With sublimation, the direction of heat flow is into the water. And with deposition, the direction of heat flow is away from the water. And the amount of heat transferred in both these processes is 2.83 times 10 to the 6 joules per kilogram. And a note at the bottom of this PowerPoint, the amount of heat transferred in the sublimation and deposition process is equal to the sum of the previous values that we've looked at, the previous two sets, the 3.34 times 10 to the fifth plus the 2.5 times 10 to the sixth. Those added together, 2.83 times 10 to the 6 joules per kilogram. So sublimation and deposition are adding the amount of heat flow in the previous two sets. Latent heat absorption, you'll come across this term several times. The heat flows into the water, and the subtraction of heat from the surrounding air causes a cooling of the air. So the three processes that are going to cool the air by absorbing latent heat are melting, evaporation, and sublimation. So when precipitation occurs and that precipitation falls into dry air, air that has a relative humidity less than 100%, if it's snow, there could be some sublimation that takes place as that ice is converted into water vapor. Or if it's liquid precipitation, it could evaporate. And evaporation is a very significant cooling process. melting. If you have snow and it's falling into air that's above freezing, that snow is going to melt and it's going to evaporate also, can also sublimate. So those three processes together can produce significant cooling when snow is falling into dry air. The opposite process is latent heat release. Heat flows away from the water, and the addition of heat to the surrounding air causes a warming of the air or less cooling than would otherwise occur. The three processes that release latent heat are freezing, condensation, and deposition. An example of less cooling than would otherwise occur is if you have a rising parcel of saturated air. It's going to cool adiabatically, but at the same time condensation is occurring, which is adding heat to the air. So that parcel of saturated air as it's rising is not going to cool off as quickly as a parcel of air that's unsaturated and rising. We'll look at an example problem. We have 4 kilograms of ice, and this melts and evaporates. And the question is, how much latent heat has been absorbed by this process? So we've got 2 processes here. We're taking this 4 kilograms, completely melting it, and then completely vaporizing it. So for our answer, we take our mass, which is the 4 kilograms, and multiply that by the latent heat of melting. Then once it melts, then we take that mass, 4 kilograms, and multiply it by the latent heat of evaporation. So we plug in our values for latent heat of melting and vaporization, add those 2 values together, and the units will be in joules. So it's a little over 11 million joules. So even with a small amount of water, you have a significant amount of latent heat that can be released or absorbed when water changes state. Next, we'll look at the virtual temperature equation. And first, go over what is the virtual temperature. You'll run across this in the book and in the lecture several times. So we'll go over what exactly virtual temperature is. Virtual temperature is defined as the temperature that perfectly dry air would need in order to have the same density as the air with moisture. At the same temperature and pressure, dry air is more dense than moist air. Remember in a previous lecture, we had a problem where we were looking at the average molecular weights of different gases, and water vapor had a relatively low average molecular weight because it's composed of hydrogen, which is the lightest element, and then it only has 1 oxygen. So put together, the H2O is relatively light compared to O2, oxygen, or N2, nitrogen. Therefore, air that is perfectly dry needs to have a higher temperature in order to have the same density as the less dense moist air. Air becomes less dense as it is warmed. And why do we use the virtual temperature in equations instead of the actual temperature? Well, here's the reason why. Using the virtual temperature makes solving thermodynamic equations easier since the constant RD, the gas constant for dry air RD, can continue to be used in equations without having to alter the R value. R would change as a function of moisture content of the air, and this would complicate the equations because a different sample of air is often going to have different amounts of water vapor within that air, so that's going to change the average molecular weight of that air. But to simplify things, we can just say the air is perfectly dry and warm that air up a little bit so that they'll have the exact same densities. So the moist air and the dry air will have the same densities. Virtual temperature and RD will often show up in the same equation. So in the hypsometric equation and the equation of state, it had both those values in there. So if you're using the value of RD, which is the gas constant of dry air, you'll want to use the virtual temperature, since the virtual temperature is a temperature that dry air has, taking in consideration the moisture that's in the air. So the virtual temperature is going to be a little bit greater than the actual temperature. The virtual temperature will be a partial degree to a few degrees warmer than the actual temperature. And given here next is the equation for virtual temperature. So the virtual temperature is equal to the temperature multiplied by these terms here, which are 1 plus 0.61 times the mixing ratio. So TV is our virtual temperature in units of Kelvin. The 0.61 comes from RV divided by RD, so it's a ratio of the gas constants and subtracted -1. And W is the mixing ratio expressed in kilograms per kilograms, and that's very important. If the mixing ratio is in grams per kilogram, you'll want to convert that to kilograms per kilogram before you insert that into this equation. Next, we'll look at an example problem. The temperature is 86 degrees Fahrenheit with a mixing ratio of 15 grams per kilogram. And we're asked, what is the virtual temperature of this air? So one thing to keep in mind, once you get to your final answer, ask yourself, is the answer realistic? A realistic answer is going to be that the virtual temperature is always going to be a little bit warmer than the actual temperature. And the more moisture there is in the air, so the higher the mixing ratio value is, and generally the greater the difference between the temperature and the virtual temperature. So with 86 degrees Fahrenheit, we convert that to Celsius, and that's 30 degrees Celsius, and then add 273 to that to get it in the units of Kelvin, 303 Kelvin. And for the mixing ratio, as I mentioned, that needs to be converted into kilograms per kilogram. So you take 15 divided by 1,000 to get 0.015 kilograms per kilograms. And now we can plug these values into the equation and find the virtual temperature. So we have the 0.015 times 0.61, and we determine that value and then add 1 to that. So in your calculator, you want to make sure that these numbers are working out as I have them here. And when this small number that you'll get here is added to 1, you'll get 1.00915. So this value here, when you're solving the equation, is always, the number is going to always be a little bit bigger than 1, because once that's multiplied by the temperature, you'll get a value that's a little bit larger. The virtual temperature is always going to be a little bit larger than the actual temperature, because we need to account for the moisture that's in the air. So we take the 303 value, multiply by 1.00915, and that is equal to 305.8 Kelvin. Or we can convert that back into the other temperature scales, 32.8 Celsius, or 91 degrees Fahrenheit. The dew point depression, the formula for the dew point depression. And when finding the dew point depression, you'll be on a constant pressure surface. For example, at 1,000 millibars or 850 millibars, right at the surface. And you note what the temperature and the dew point are at that pressure surface. And the dew point depression is the temperature minus the dew point. So since the temperature is always bigger than the dew point depression is always going to be a positive number, or it could be 0 if the air is saturated. Relative humidity. Surprisingly, relative humidity can be fairly complicated to calculate. The relative humidity is not simply just taking the dew point divided by the temperature. There's some involved mathematics that go into determining what the relative humidity value is. There are two equations here for the relative humidity. Relative humidity is 100% times the mixing ratio divided by the saturation mixing ratio, or 100% times the vapor pressure divided by the saturation vapor pressure. And we've already discussed the vapor pressure and mixing ratio values today. And we can find what those values are and use the Clausius-Clapeyron equation to find what the relative humidity value is. So these are the equations that you were given earlier for mixing ratio, saturation mixing ratio, the vapor pressure, and saturation vapor pressure. Next, we'll look at lapse rate, starting with the definition of the lapse rate. Lapse rate is a change in temperature with a change in height expressed as dt over dz. So that d symbol means that it's a change in temperature, and dz is the change in height. So for example, the temperature at 700 millibars is 2 degrees Celsius, and the temperature at 500 millibars is minus 15. The vertical distance between these two pressure surfaces is 2,450 meters, and we're asked what is the change in temperature with the change in height in units of Celsius per kilometer. So we first determine what the temperature difference is. We have a 2 and a minus 15, so the temperature difference is 17. And then we were given what the vertical distance was, and we're going to convert that into kilometers since we want the final answer to be in Celsius per kilometer. So we take the 17 Celsius, which is the change in temperature, divided by the change in height, and divide those, and that produces a value of 6.9 Celsius per kilometer. The potential temperature is the temperature a sample of air will have if it's brought to the 1,000 millibar pressure surface at the dry adiabatic lapse rate. And there is the equation, once again, for the potential temperature that we've looked at previously. The temperature that's plugged in this equation needs to be in kelvins. The pressure will be in millibars. And the other terms are constant, the gas constant for dry air and constant pressure process. We're going to take it a step further today and go over what is known as the equivalent temperature. The equivalent temperature is the temperature air will have after latent heat is converted to sensible heat. So we're going to condense all the moisture out of the air, and condensation is a warming process that's going to warm the air. In air with moisture, the equivalent temperature will be greater than the air temperature due to that condensation release. And the equivalent temperature is going to be expressed in units of Kelvin. And the formula for the equivalent temperature, the equivalent temperature is equal to the actual temperature, and then this E here, which the E this time stands for the exponential function. So you have to multiply these values out here first and then take the exponent of that value and then multiply it by the temperature. So for an example problem, an air parcel at 800 millibars, so 800 millibars, has a temperature of 5 degrees Celsius with a dew point of 0 Celsius. And we want to find what the equivalent temperature of this air is. And we need to know what the mixing ratio value is, so we're given that the mixing ratio is 4.8 grams per kilogram. And these constants here, we have the W here, which is the mixing ratio. L is that latent heat value. Cp is a constant, at constant pressure gas process, and then times the temperature. On the overhead camera, we'll look at how to solve this problem. There's the equivalent temperature and our equation. We have an exponential function here, so we got these four terms up here that we need to multiply and divide out, and then take the exponent of that value. The temperature is 5 degrees Celsius, and we need to convert that to Kelvin, so we add 273, so that's 278 Kelvin. L is our latent heat value. This is a condensation process, 2.45 times 10 to the 6 joules per kilogram. Cp is 1,004 joules per kilogram per Kelvin. And then our mixing ratio, we need to express that in kilograms per kilogram. So that'll be 0.0048. Once these terms here, the L is multiplied by the mixing ratio and divided by the 1,004 times 278, once those are multiplied and divided out, you'll end up with this value here, 0.042133.624. Let the calculator go out as many digits as it can, and then take the exponent of that number, and then once you have that number, then you multiply that by 278, which is our temperature. And once that is done, you'll end up with an equivalent temperature of 290 Kelvin. So we had an original temperature of 278. We took all the moisture in the air, condensed it out. That releases that latent heat. After all that latent heat is released, we end up with a value of 290 Kelvin. And down here, I have written what you should get on your calculator when you take E of this number here. You'll end up with 1.043033844. So when you take that value here and multiply that by the 278, you'll get the 290 value. This, in later lectures in the class, we'll go over how this can be solved on the SKU-T log P, where you don't have to do any of the mathematics. The SKU-T log P is the mathematical solution to a lot of these problems that we've gone over. And I did this problem on the SKU-T log P and got a value of 291 Kelvin, so it's very close. So that confirms that we did the right process here. Okay, we've talked about the equivalent temperature. Next on the PowerPoints, we're going to go over the equivalent potential temperature. So we've added two words here in front of the temperature. It's not just the equivalent temperature, it's not just the potential temperature, it is the equivalent potential temperature. And this is found the same way as the equivalent temperature, except the parcel is brought to the 1,000 millibar level after latent heat is converted into sensible heat. We'll look at the formula now for the equivalent potential temperature. Another term for equivalent potential temperature is theta E. So we have a theta E value that is equal to the potential temperature and then multiplied by the exponent of those same terms that we looked at in the equivalent temperature. So we'll look at an example of finding the equivalent potential temperature. An air parcel at 800 millibars has a temperature of 5 degrees Celsius with a dew point of 0 degrees Celsius. What is the equivalent potential temperature of this air? And once again, we're given the mixing ratio value of 4.8 grams per kilogram. So this is similar to the problem we had before, except we're going to take the parcel all the way down to 1,000 millibars and figure out what that value is. So on the overhead camera, we'll go over the solution to this problem. Here is our equation. We have the theta E, equivalent potential temperature, is equal to the potential temperature. The symbol here, theta, means potential temperature, then multiplied by the exponent of those 4 terms we looked at earlier. For the potential temperature, which is here, the equation we need for that is the temperature times the 1,000 over P to the 0.286 power. So our temperature is 278. So it was 5 Celsius. We added 273 to that to get 278. Our pressure is 800 millibars. So when we plug these two values into this equation, we get a potential temperature of 296.3 Kelvin. So now we can plug that value into the theta E equation to find the equivalent potential temperature. So we'll take the 296.3, which is our potential temperature in Kelvin, and multiply that by the exponent of the number that we found here, the L divided by mixing ratio divided by Cp times T, that we found in the previous problem. So this part is the same as the previous problem. We're just multiplied by the potential temperature instead of the actual temperature. And when this calculation is performed, you'll get an equivalent potential temperature of 309 Kelvin. And on the PowerPoint, there's another equation, a more simple equation that we can use to find the theta E value. And that equation is the theta E is equal to the theta value plus 3 times the mixing ratio, where the mixing ratio is in grams per kilogram. Now we'll go right back to the overhead camera and look at a solution using that equation. Using these different equations, since this is a little bit more simplified equation than what we have up here, the answers may be a little bit off, but they should be fairly close together. So if we take our potential temperature 296.3 and add 3 times the mixing ratio, we get a value of 311 Kelvin. The theta E can also be solved on the skew-T log P. And when I solved it on the skew-T log P, I got a value of 310 Kelvin. So 3 different methods of solving this problem had a 309, 311, 310. So all values are fairly close together. That's a good indication that we did this problem right. And for testing purposes, I'll spread out the answers enough so that you'll know which answer is the correct one when you're given a multiple choice type question. Next on the PowerPoint, we'll look at the hydrostatic equation. This equation gives the rate of pressure decrease with height, and the formula is dP. The dP stands for change in pressure divided by dz, where dz means the change in height. So the change in pressure with the change in height is equal to a negative sign times the density times gravity. So change in pressure divided by change in height is equal to a negative density times gravity. And the negative sign there is to indicate that as you're going up in the troposphere from the surface, that the pressure is going to be decreasing. So for an example problem, does dP over dz decrease more or less rapidly in a cold troposphere as compared to a warm troposphere? And our solution, the density in cold air is greater. Since the molecules are not moving as quickly, they're going to be closer together, a higher density of colder air. Thus, when using this equation here, the density value, since this density is going to be greater in cold air, then the dP divided by dz is also going to be greater. The gravity is a constant. We can treat that as a constant. So the only variable that's really going to change is the density. So if this is more dense, then these two variables multiplied by each other is going to be a higher value when density is greater. So the dP divided by the dz is going to be greater in cold air. So the height of the troposphere is less. Another way of saying that, the thickness of the troposphere is less in cold air. Thus, the change in pressure with change in height is more rapid. Since the thickness is less, you don't have to go up as high to have a significant pressure decrease when you're in cold air. The last thing that we want to do is have a quiz. And we'll go over the questions and answers to this quiz. What you need to know for the problem is the current conditions in Denver, Colorado are a surface pressure of 850 millibars with a temperature of 54 degrees Fahrenheit and a dew point of 25 degrees Fahrenheit. And we want to determine what is the relative humidity of this air using the Clausius-Clapeyron equation. And then we want to find what the virtual temperature of the same air is. Then we want to find what the potential temperature, equivalent temperature, and equivalent potential temperature are of this same air in Denver. So we'll go to the overhead and solve the first problem. We are given a temperature of 54 degrees Fahrenheit. This needs to be converted into kelvins when using these equations that we've gone over today. 54 degrees Fahrenheit is equal to 12 degrees Celsius is equal to 285 Kelvin for our temperature. Our dew point is 25. That converts to -4 in Celsius, and 269 Kelvin for the dew point, and the pressure was given as 850 millibars. So we have our Clausius-Clapeyron equation, and there's two forms of the equation that I'm showing here, and they're exactly the same with only one minor difference. The one at the top is for the vapor pressure, and when using the Clausius-Clapeyron equation to find the vapor pressure, you plug the dew point value in for T. If you want to find the saturation vapor pressure, then you have to plug in the temperature value for T. So everything is solved the same exact way. It's just these one equation, you plug the dew point in, and one equation is the temperature, and we have determined above here what the temperature and the dew point are of this air. Once we have solved both these equations, for the vapor pressure and saturation vapor pressure, then the relative humidity is going to be vapor pressure divided by saturation vapor pressure times 100%. So we'll start by finding E, the vapor pressure. So we put in the dew point value, which is 269 Kelvin, into this equation. We take the L divided by RV, which earlier in the lecture you're given that value, and then multiply by 1 over 273 minus 1 over 269. And when these terms are multiplied out on your calculator, you should get a negative 0.289828899. And then you want to take the exponent of each side. So on the left side, taking the exponent of the natural log cancels that out. And so you're left with taking the exponent of the right side of the equation. And when you take the exponent of this number, you'll end up with 0.748391607. And then our last step is to multiply both sides of the equation by 6.11. And after that is done, we'll end up with a vapor pressure of 4.57 millibars. And now to find the saturation vapor pressure, we use the same equation, except we now plug in the temperature for T here. And we go through the same process that we did above, and when that's done, we'll end up with a saturation vapor pressure of 13.88 millibars. So to find the relative humidity, we take the 4.57 millibars and divide by the saturation vapor pressure of 13.88 millibars and multiply by 100%. And so we determine that the relative humidity of this air is 33%. So you can see how involved it is, the process here of finding the relative humidity of the air. There's some computer programs online that you can go to and put the temperature and the dew point in, and that'll give you the relative humidity value too, and it's solving this Clausius-Clapeyron equation for you. Next, we wanted to find what the virtual temperature of the air was in Denver. So to find that, we'll take our equation, the virtual temperature is equal to the temperature times 1 plus 0.61 W. So we need to find what W is, and if we can do that, then we can find what the virtual temperature is. We know that the vapor pressure we just solved in the Clausius-Clapeyron equation, we found that the actual vapor pressure is 4.57 millibars. So since we know what this value is, we can use another equation that was given earlier, the mixing ratio equation, 0.622 E divided by P minus E. So we'll plug in the 4.57 in for E in both places here in the equation, and we end up with a mixing ratio value of 0.003362242, and this is in units of kilograms per kilogram. And we have it in kilograms per kilogram to plug it back into the equation. So we have the virtual temperature is equal to 285 Kelvin, and then we multiply that by the 1 plus 0.61 W. So this is the temperature of that air in Denver that we already determined previously, 285 Kelvin. And then we're going to put this mixing ratio value into the equation here and solve. And when that's done, you'll end up with the value of 285.6 Kelvin. And converted back into the other temperature scales is 12.6 Celsius and 54.7 Fahrenheit. Usually it's going to be left in units of Kelvin. Next, we want to determine the potential temperature of the air. That's the temperature times 1,000 divided by P to the 0.286. So 285 is our temperature. You take 1,000 divided by 850 and you'll get a number. Take that to the 0.286 power. So you have one number here multiplied by 285 and you'll end up with 298.6 Kelvin for the potential temperature. Now for the equivalent temperature. We take the temperature, which is 285, and multiply that by the exponent of L times W divided by Cp times T. Our W value we found just previously, the 0.003362242. Our temperature is 285. And the others are constants that we looked at earlier. So multiply and divide those terms out, and you'll get 0.028788331. Take the exponent of that number and multiply by 285, and you'll end up with 293 Kelvin for the equivalent temperature. Now for the theta E, the equivalent potential temperature, there's two equations that we went over to find that. You can first take the potential temperature and add 3 times the mixing ratio, with the mixing ratio this time in grams per kilogram. So our potential temperature that we found here is 298.6. So we put 298.6 plus 3 times the mixing ratio value, which was 10.08. Add those together, we get a value of about 309 Kelvin for equivalent potential temperature.